Hello, my name is Carlo Carandang, and I'm a psychiatrist and data scientist. Today, I will talk about AI and big data in psychiatry, an introduction and overview. Learning goals for today. First, I will help you understand AI and big data in psychiatry. Secondly, I will help you understand big data systems for psychiatry. And last, I will help you understand machine learning algorithms for psychiatry AI applications. So if you can remember back to the blockbuster movie I, Robot, starring Will Smith back in 2004, we get our first glimpses into the AI, bots, and psychiatry and how they merge. And this was back in 2004 where the idea seemed far-fetched. However, this is the year 2020 and it's not as far-fetched as it may have seemed back then. So here's the scene where Will Smith, who plays Detective Spooner, meets Dr. Calvin, and Dr. Calvin's a psychiatrist who specializes in AI and robotics. So here's the interaction. Detective Spooner: so, Dr. Calvin, what exactly do you do around here? Dr. Calvin: my general fields are advanced robotics and psychiatry, although I specialize in hardware to wetware interfaces in an effort to advance USR's robotic anthropomorphization program. Detective Spooner: so what exactly do you do around here? Detective Calvin: I make the robot seem more human. Now, wasn't that easier to say? No, not really. So again, this back then it seemed far-fetched that you'd have a psychiatrist that would actually make the AI robot seem more human, but it's not so far-fetched in 2020. And this was 16 years ago. A lot has happened in AI and big data to make this more reality. So I will discuss how far we've advanced from when this movie first came out, where it seemed far-fetched. So we do have the world's first mental health chatbot, which came out in 2018, and this chatbot is called Wobot. So Wobot is basically a bot that takes information from the client, and the client then is prompted by Wobot regarding how they're feeling, what their moods are, their sleep patterns, how they're eating. So various mental health parameters are asked by Wobot, and based on those parameters that are entered, the Wobot can tell you if you're sleep deprived, or if you're anxious, or if you're depressed. And actually, this Wobot was actually designed and built by Stanford researchers. And there's studies showing that it's effective for anxiety and depression, for mild anxiety and depression. So this is the start of a revolution in mental health, where we now have the world's first mental health chatbot called Wobot. And actually, Wobot is actually easy to assess. It's actually, you can assess it via Facebook Messenger interface. So you interact with Wobot via Facebook Messenger, and Wobot will then check in on you on as often as you'd like, and will go away if you tell it to go away. So check it out. Just Google Wobot and you can try it out. I actually have used it and I continue to use it. It helps for if you're having sleep problems, if you're having some mental health issues, Wobot can help you. And this is a form of cognitive behavioral therapy for which it can help for things such as sleep problems, depression, and anxiety. Mild cases. But if you're having more difficult symptoms, then you should, of course, see a doctor, therapist, or your family doctor for a referral to one. So let's go through some definitions of what artificial intelligence actually is. So AI, also, which is short for artificial intelligence, aims to mimic human cognitive functions. So AI is built from machine learning for structured data and natural language processing for unstructured data. Another concept that comes into play is big data. So big data, when we're talking about big data, we're talking about petabytes of data. So 1 petabyte is equal to 1024 terabytes. So petabytes are in the order of millions of patient records. So basically, you go into a typical hospital database, and typically you'll find millions of patient records. So there you're talking about big data, petabytes of data. We also want to differentiate AI and machine learning from hard coding. So hard coding is where you take explicit coding instructions to carry out a task. All right? So that's hard coding, where you code specific tasks line by line via code. Okay? The difference between hard coding and machine learning is that machine learning, the computer uses data, algorithms, and statistical models to perform a task without being hard-coded. So it relies on patterns and inference. So rather than being hard-coded, so rather than putting in the rules if, and, or, else, which you do in hard coding, for machine learning, you're using the computer to actually look at the data, build algorithms, and use statistical models to perform a task from the data without it being hard-coded for the business logic or the rules. Another concept to realize is that in machine learning, you have to have some knowledge. You have to have knowledge of linear algebra, as linear algebra is the basis for machine learning. So linear algebra terms such as scalar, which is magnitude x. You need to know a vector, which has both magnitude and direction, x and y. So again, scalar is just magnitude, it's x. Vector is x and y, which is both magnitude and direction. And a matrix is an array of elements in a row and columns. Okay, so matrix is an array of elements in row and columns. So on this slide, I will take you through how clinical activities and the data that's produced from clinical activities can turn into machine learning and artificial intelligence, which then gives us the outputs for how we make some clinical decision making from those clinical activities and inputting it to machine learning algorithms that which on a whole defines artificial intelligence. So let me take you through this. So you have here clinical activities. This is where it starts. And then you have these clinical activities, which include screening, diagnosis, and treatment. This could be in the form of imaging, genetic data, or electrophysiological data. These type of data, such as imaging, genetic data, and electrophysiological data, such as EKGs, such as O2-SAT, such as all your laboratories, these then form part of the data sets which can be fed into machine learning algorithms to actually detect patterns, such as if you have say if you have heart disease, then it'll show a certain pattern for EKG, for laboratories, genetic markers, and so forth, which can then help the doctor to diagnose something like heart disease better in its subtypes. So it's just a way to assist the doctor to identify patterns, because really at the end of the day, what's a doctor doing? A doctor is actually taking an inventory of symptoms, taking the inventory of the objective measures from the lab data, from the physical, from the EKG, and putting this all together for a pattern recognition that fits a certain diagnosis. So that's what doctors do all day. So what machine learning does, it actually helps assist in this process to identify these patterns with the doctor, so it can assist with diagnosis. So that's one way where clinical activities generates data. Another way that clinical activities generates data is through clinical notes in human language. So you take the electronic medical records, or maybe you can just take the handwritten notes from the doctor, and you can, if it's in the EMR, it could be fed directly into the computer, or if it's paper form, this can be transferred to OCR in the PDF form, and this could be transferred then to via OCR to digital form where the computer can read it. So in whatever form clinical notes take, you can input it to the computer, and you can take what's called natural language processing, which basically identifies the different parts of the structure of a corpus of the clinical note, where it can identify sentences, identify keywords, what are subjects, what are verbs, what are things that pop out on a page and is repeated on different pages. So natural language processing actually makes meaning of the text by dissecting the actual words, sentences, and how they come together. And then the outputs of natural language processing then also forms the corpus, this entire corpus here, which then can be fed to machine learning algorithms, and then it leads to these outputs, and the outputs are generally, maybe it'll classify, maybe high-risk patients. It might help assist the doctors stating that this might be high risk for a certain type of heart disease, as I mentioned before. And basically, it's just to help the doctor with diagnosis and treatment planning. So that's what machine learning can do for the doctor and the psychiatrist when treating mental health patients. And this whole thing then is called artificial intelligence. This whole thing where this whole process is artificial intelligence, right? So there have been multiple publications of machine learning in psychiatry recently, and here I just give an example of some of the ones that have stood out for me. So the first one is reevaluating the efficacy and predictability of antidepressant treatments, a symptom clustering approach in JAMA Psychiatry in 2017. So clustering is a form of unsupervised learning, which I will go into detail later in this talk. And then you have the second one, multi-site prediction of 4-week and 52-week treatment outcomes in patients with first episode psychosis, a machine learning approach. So you're seeing these titles with machine learning in psychiatry research. It's exciting. So, and these are in prominent journals. This is in Lancet Psychiatry. And then the third one, you have predicting response to repetitive transcranial magnetic stimulation in patients with schizophrenia using structural magnetic resonance imaging, a multi-site machine learning analysis. Again, machine learning's being used. So machine learning is here to stay. As you can see that it's being showcased in research studies published in major psychiatric journals. So this is quite exciting. So just stay tuned for more research into AI in psychiatry, because it's even hitting our psychiatric journals in studies. It's quite exciting. So in this talk, I'm going to be talking about using big data and big data systems. Then I'll be talking about algorithms, and then how these algorithms can then solve psychiatry problems. So this is what I'm going to be talking about today: big data systems, algorithms, and how these algorithms can help solve psychiatry problems with Psychiatry AI applications. So let's first go into what big data is. So when we're defining big data, we're really talking about the 4 V's of big data. So the first V of big data is volume, the scale of the data. So when we're talking about big data, we're really talking about, we're going into the petabytes of data, as I talked about earlier. Petabytes of data is just basically looking at a typical hospital database, which has millions of patient records. And these millions of patient records are just in the order of petabytes. So this is what you call big data. Just take the entire database, and that is the volume of big data. So just think of a hospital, typical hospital database, a big hospital, okay, say at least 500 to 1,000 bed hospital. That's big data, their database. The other V, besides volume, there's also velocity. So, um, so not only are we looking at the volume of data, we're also looking at the velocity of the data. So like streaming data. So when you're looking at streaming data, you're looking at things like EKGs that are you're doing like monitor all the monitors that you see in the hospital that's hooked up to a patient. So they could be EKGs, O2 sats. It could be laboratory results. So these things, especially things that are continuously being measured, this is an example of streaming data, and streaming data can go real fast. So not only do you have to contend with the volume of your patient database at the hospital, you're also looking at the velocity of that streaming data from all your electrophysiological machines that are taking data from your patients every day. And you got to keep up with that constant streaming of such data, all right? The third V of the four V's of big data is variety. So data could come in different forms. It can come in the form of social media. It could come in the form of videos. It could come in the form of electrophysiologic readings. It could come in the form of wearables, where you're wearing watches that can detect heartbeats. In the hospital, it's about all the sensors you hook up to the patients, all the laboratories you take on the patients, the x-rays, videos, clinical notes. So those all are just varieties, different forms of data. So not only do you have to contend with the volume of the data and the velocity of the streaming data, you also have to contend that the data can come in various forms that you also have to somehow manage and process. And then here, sorry, my little picture here is blocking this bubble, but the last one is veracity. So veracity, so the four V's of big data, the last V is called veracity. So veracity is the uncertainty of the data. So really, we're really not sure. A lot of the data we take, we're not sure if they're valid or not. So in the hospital settings, this is less of an issue because the sensors we use on patients were usually they're usually built, designed to be accurate. However, there are some errors that come when measuring anything. So we have to contend that any data that we take will still have some error that we have to contend with, and then we have to, when we're doing analysis on such data, we have to contend that this data may have errors in it, because you know of the old adage, garbage in, garbage out. So when we have data that you can't really verify and you're uncertain about, it really leads to less intelligence. So so this is the four V's of big data that we have to contend with: volume, velocity of streaming data, the variety of the different forms of data, and the veracity regarding the uncertainty of the data. So these are all things to contend with when we're looking at big data. So with regards to big data in healthcare, there is a potential of, there's $300 billion potential annual value to healthcare if we could harness big data and AI for healthcare. So if you look here, these are amazing. 100 and so when you look globally, just for clinical decision support, we could harness $165 billion just from that for big data and AI. 108 billion from personalized medicine and clinical trial design. 47 billion from fraud detection. So if we can use big data and AI to detect fraud in our healthcare systems, then we could save $47 billion. We could save $9 billion from public health surveillance and response. We could save $5 billion from digitization, aggregation, and automation of patient records. So it is estimated that 30% of the data that is produced worldwide is from healthcare. So healthcare not only produces the most amount of data than other fields, professional fields. What we know in healthcare is if we can harness big data and AI, then we can save up to $300 billion annually to healthcare if we're able to harness this. Okay, so it's very important that we learn about AI and big data in healthcare, and specifically to psychiatry, which I will focus on momentarily. So, what's the big deal about data? Well, the big deal is data in itself is useless. So, data that's just sitting in your hospital databases, in your outpatient clinics, data that's just sitting there is nothing. So it doesn't really give you anything if it's just sitting there. So in order to make data useful, you have to start then classifying the different data points you see in your data set. So here is an example where you start classifying purple dots from green data points. So this leads to information. A level up from this is knowledge, where you start actually taking these labeled data sets and actually try to make relationships between, you try to form these relationships, or we call these, in graph analysis, we call these edges, the connections between nodes. So this then forms knowledge as you're now able to connect the dots, so to speak. One order up from that is insight, where from knowledge you gain insight, from where you go, instead of just these just overall connections from network graph analysis, you can go and actually see that one part of the nodes is actually connected to another part of a node. So that leads to insight. So we know that these two nodes are connected somehow. Okay, and then ultimately this can lead to wisdom, where in this case you see that these two nodes, you know the exact circuit from which they are connected, and this then gives us wisdom. So this is just an example of how we just go from plain data, which gives us nothing, to wisdom, as you see here, and everything in between. So with regards to psychiatry, psychiatry generates lots of different kinds of information. So in psychiatry, we have the clinical history, patient demographics, diagnosis, procedures, such as psychotherapy, ECT, TMS. Also the procedures, in addition to procedures, we have medications, lab results, and clinical notes. Also, what you're starting to see now is that you can have on-body sensors and other devices that patients wear to detect activity in their behaviors. You can also look at their social media feeds, which actually gives clues into their thoughts, moods, reactions of the social network to the patient. And then we have real-time data sources such as blood pressure, temperature, heart rate, all the electrophysiological sensors I was talking about earlier. So things such as blood pressure, temperature, and heart rate, it gives a clue into the sympathetic nervous system and connection to the amygdala-driven fear response. And the stress response is actually quite prominent among mental health patients and what we deal with as psychiatrists. And lastly, we have drug dispensing and all the information we gather from psychiatric inpatient stays. So psychiatry generates lots of different kinds of information, as I outlined here. So now that I've talked about big data, talked about the 4 V's of data, that's volume, velocity, variety, veracity, right? Then we're talking about petabytes of data. Next, I'll talk about big data systems. So these are the things that help to process this big data and how to provision this so that the data scientists can then build the algorithms here, which can then solve psychiatric problems here in the form of Psychiatry AI applications. So in the next section, we'll talk about big data systems. So Hadoop is the platform that administers MapReduce to process and analyze big data. So here we have data in a database. And here we have patient 1 and patient 2 in the database. And then what we do in MapReduce is that we map from each patient what their diagnoses are. So in patient 1, we map major depressive disorder and give it a score of 1 because there's one instance of major depressive disorder for that patient. And then the patient also has generalized anxiety disorder for patient 1, so we also give GAD a score of 1 for one occurrence of GAD. In patient 2, we map their diagnosis, and their diagnosis has post-traumatic stress disorder, so we map that as one occurrence in that patient. And then the patient also has major depressive disorder, so we map that as 1 in patient 2. Okay, so when we're looking at population data, such as all the data in a hospital database, Hadoop is a way to do population descriptive statistics such as histograms, frequency, occurrence of certain categories such as disease processes in patients. Just when you want to just look at this from a population point of view in your database, you can utilize Hadoop to actually do this at scale for your entire database, and it uses MapReduce. So the first step in MapReduce is to map out what each patient has for diagnosis as an example for things that this can do, because MapReduce is a form of counting and ordering on big data, such as all the data in your hospital database. So after you map the various disorders, psychiatric disorders in each patient, here I'm just giving patient 1 and patient 2 as examples. We map out the different disorders. So again, this is patient 1 and patient 2. Now what we do then is, after we map all the disorders in the patients, then we shuffle this and we combine them all. So you see here for major depressive disorder, there's 1 here, and we also have major depressor here. So what happens is we shuffle this mapped out disorders and give major depressive disorder. We just collate, we just basically sum up this to 1, 1 as major depressive disorder. GAD, there's only 1 for GAD, so we put 1 there, and there's only 1 for PTSD, so we put PTSD 1 here, right? So after we shuffle and we give the counts for each disorder, we then reduce it. So in the reduce phase, what we do is we then sum up all the counts. So here, major depressive disorder occurred twice, so we give it a count of 2. GAD has a count of 1, and PTSD continues to have a count of 1. So this is the reduce phase. So this is a way, as you can see, this is a nice way to have histograms, frequencies of various disorders in your population database, in your hospital database. And a quick way to do that for your entire database is to use MapReduce in Hadoop. So this is very, very handy. However, there are pros and cons of MapReduce in Hadoop. So a pro is that Hadoop can work with big data using MapReduce computations, as I outlined in the previous 2 slides, especially when you scale that to beyond 2 patients. Of course, maybe you want to scale it up to 1 million patients in your database, and then you could find out the true power of Hadoop and MapReduce to actually do descriptive statistics on your population database for your hospital. However, a con for Hadoop is that it is not good for iterative computations such as required for machine learning. So if you want to do any advanced machine learning or deep learning, then Hadoop is not the tool to use. Hadoop is just more for descriptive statistics for your big data, for all the data in your database and your data lakes. So as I mentioned, another pro of Hadoop, it works well for billions of records that you want a histogram, odds ratio, or prevalence. And then pro and con, Hadoop uses distributed hard disk to store massive data, but it also makes it slow for iterative computation, just because hard disks can be slow because it depends on the spinning of actual physical disks. So that's the bottleneck for Hadoop, that the data is stored on hard disk still. So the speed is actually, the bottleneck is dictated by those hard disks, the physical limitations of those hard disks, because they have to spin in order to read and write data. So next I will talk about Spark. So Spark is the platform for machine learning of big data. So Spark uses RAM. So it's faster than Hadoop MapReduce, data stored on magnetic disks. So as I mentioned before, Hadoop is stored on magnetic disks in parallel. However, Spark uses RAM, which is faster than magnetic disks, because RAM basically is stored in memory in your computer on electrons, basically. So RAM is the speed of electrons, so it's much faster than physical disks of Hadoop MapReduce. So this is why Spark is advantageous platform for machine learning, because Spark uses RAM in parallel. So basically they stack a lot of machine servers together and they utilize the RAM of those machines in parallel. Whereas Hadoop uses those machines in parallel, uses the hard disks. So hence you see the value of Spark for speed, because it uses RAM. And Spark is fast enough to perform iterative computations needed by machine learning. And Spark uses, as I mentioned before, distributed RAM to handle massive computations of big data. So here you have Hadoop and you have Spark. So Hadoop and Spark can be provisioned in the cloud. It could be provisioned in Google Cloud Platform, Azure, or AWS, Amazon Web Services. So that's if your hospital uses the cloud. Now there's some hospital settings and government settings where they don't want to put confidential sensitive patient information on the cloud. So you can actually have Hadoop and Spark on premises. We call them, these are on-prem solutions. So you can actually build these on premises, but it takes a lot of expertise and a whole IT infrastructure to keep this going, and data science expertise to keep this going with your data engineers to build and maintain this. So if you decide not to go to the cloud, then you have to have the right IT professionals to architect this and maintain this on-prem in your hospitals. So next I will talk about algorithms. So I talked first about big data. I also talked about big data systems such as Hadoop and Spark. So once you process and provision the data in these big data systems, then you need to start building algorithms. And that's what a data scientist does. Next, I'll talk about supervised versus unsupervised learning. So when you're talking about supervised learning versus unsupervised learning, these are the two main types of training for machine learning algorithms. So when you're looking at algorithms, you're looking to choose between supervised learning versus unsupervised learning. So in supervised learning, when you have a discrete variable, so say you want to say someone's at risk for depression, yes or no. So you're actually trying to classify something as yes or no for depression, for risk of depression. So this is a form of supervised learning. So basically you'll have a data set where it has different features of, say, maybe it'll have features of depressive symptoms such as disrupted sleep, such as suicidal thoughts, such as low mood. So You label that as a 1 for high risk for depression, and then on the other side you'll have data that might look like sleeping 8 hours per day, mood neutral or happy, appetite good. So you'll label that as a 0. So zero risk for depression. So that's what you call discrete supervised learning. It uses discrete variables such as 0 or 1, 1 having high risk for depression, 0 having no risk for depression. And you can, if you have such labeled data, label a data set 1 or 0 based on some features such as I just described, then you can train an algorithm via supervised learning to actually train it to help it classify on data sets to say if it's either 1 or 0, if it's either 1 high risk for depression or 0 no risk for depression. Another type of supervised learning is when you use continuous variables. This is called regression. So maybe you're looking at, you're an administrator and you're looking at hospital costs per psychiatric patient on an inpatient unit. So say someone with schizophrenia has costs of $10,000 for a hospital stay, whereas someone with anxiety has a hospital cost of $1,000. So you start to, so when you look at costs, that's a continuous variable, and then maybe you want to plot this with costs of other patients with different diseases, and then you can apply supervised learning to this, having the outcome variable as cost for the inpatient stay, and this is supervised learning with a continuous variable, and that could be an example of regression algorithm that you build with that example. So now we go on to unsupervised learning. So when you have discrete variables, so in clustering, what happens is you basically try to group things that look alike or stand close to each other, and so these things tend to cluster when you try to map it out. However, you don't know the names of these clusters, so that's why it's called unsupervised learning. You just know they're similar to each other and you're different from the other clusters of nodes, but you just don't know the names yet. So in exploratory work, you often do unsupervised learning for discrete variables such as clustering to actually see what you got, see what is looking the same, see what looks different. Although you don't know what the labels are for those clustered nodes, you know that they're the same with things that lie close to it, and you're different from other nodes that are far from it. When you have unsupervised learning with continuous variables, then you're looking at dimensionality reduction. So these are just more advanced algorithms that are beyond the scope of this talk. So here we have machine learning. As I said before, machine learning has two different types of learning. You've got supervised learning, where you develop predictive model based on both the input and output data. So basically you have the input features and you have what their labels are, like I said, 0 or 1. Having high risk for depression, 0 for no risk of depression. So you can develop, in supervised learning, you could develop predictive models based on both the input and output data. Whereas in unsupervised learning, like I said before, you can group and interpret data based only on the input data, but you don't know the labels. So you don't know any of the outputs. You don't know what the dependent variable, the dependent variables are, because you don't know what the labels mean. You only know that you can only group and interpret data based on the input data. So this is unsupervised learning. So again, you see here with supervised learning, you have classification and regression as algorithms, and for unsupervised learning, you have clustering as a type of algorithm you can use. So again, classification here in this example here, you got feature 1 and feature 2, and then you have this line here that divides the two groups. So anything on this side is not spam, and anything on this side of the line is spam. So that's a form of classification because you know the labels of those two groups that divide based on that dotted line. You know that below that line is spam and above that line is not spam. So here's an example of regression in the middle here. Regression is where you have continuous variables such as price. I was mentioning hospital price. Here we'll look at we look at various features. Maybe the feature could be different diagnosis. And I was saying schizophrenia might be the higher cost, anxiety might be the lower cost. So when you plot this against a line, you could predict based on a feature. So maybe you give it a different diagnosis, that'll predict what the price is based on the data that you trained it on previously. So this is regression. And then lastly, for unsupervised learning, this is clustering, where, like I said before, you know what you know that these green balls actually look alike. They are near to each other and they segregate together, and they are different from these red balls that are similar to each other but are different from the green balls. However, you don't know what the labels are, so you might just call it C1, C2 for now until you figure out what they mean, what the labels really are. But that's why it's called unsupervised learning, because you don't know what the labels are. You don't know the output data. So here's a graphical illustration of unsupervised learning, supervised learning, and semi-supervised learning. So you see here, this is when you just have the input data set X. This is called unsupervised learning because you don't have any outputs, you don't have any labels for this X, so all you have are features. So this is called unsupervised learning. In the middle here, this is supervised learning because you have the features X and you have the labels Y. So for each, so here you'll have each line here will be patient rows. So each of these rows represents a patient record, and then you'll have columns here that represent, this is X1, X1, X2, and so forth. So these might be things like maybe symptoms of depression, like sleep, hours of sleep. It could be just different mood. It could be severity of appetite problems. It could be other variables, other features of your disease process that you might record in a patient record. And so again, each row is a patient, each column is a patient feature, and then with each, here's the Y could probably be, maybe you want to have this as the diagnosis. So Y is the diagnosis. And so each patient row is associated with a Y diagnosis. So this is an example of supervised learning where you have all the features X and you have the dependent output variables Y. So it could be like features of a disease, symptoms for each patient, and Y is the diagnosis. Supervised learning. Okay, erase that. And lastly, we'll talk about semi-supervised learning. So this is where you have all these features of patients, all these patient rows here, right? However, you don't have labels for all the patients, so you just have labels for maybe these three rows that coincides with here, right? So you could still use this to give you information about what these might be because you have this. So basically this is called semi-supervised learning. So you have labels just for a portion of the data set, for a portion of the patients, but not for all the patients. So let's talk about classification. So a classification algorithm takes the input X, which is in the matrix, okay? And for example, every row in this matrix represents a patient, right? So when I'm talking about a patient, each row here represents a patient. And every column of this matrix represents a feature. So again, it could be a symptom of the disease. It could be things such as cost of hospital stay. So whatever it is, you can just in a typical patient record, you might, or it might be an administrative record, or it could be a combination. These are features. So the columns are the features of the variables that you take account of for each patient, which are these rows. Okay. And the classification algorithm will map this input feature matrix, so we call this the input feature matrix, into a set of discrete outcome Y, right? So here we have the outcome matrix Y, and again, this could be things, here I'll just say, for example, these Y vectors indicate whether the patient had treatment-resistant depression or not. So this might just be a 0 or 1. So 1 being having treatment-resistant depression, 0 being not having treatment-resistant depression. So we want to learn this function f. We want to learn this function f that mapped input x to the target outcome variable y. So this is called classification, and here is the equation for it. So next we'll talk about regression, which is another form of supervised learning. This time we're going to use continuous variables. So for supervised learning with continuous variables, this is an example for it would be regression for an algorithm. Whereas in the previous example for classification, that's basically supervised learning but with discrete variables. So classification is with discrete variables, whereas regression is with continuous variables for under the umbrella of supervised learning. So in a regression algorithm, we take an input X, which is in the matrix. So again, we have patients here. So for example, every row in this matrix represents a patient, right? So every row represents a patient. And every column of this matrix represents a feature. So again, symptoms, whether or not they had sleep problems or mood problems, etc. And then say this regression algorithm will then map this input feature matrix X into a set of continuous outcome Y, right? So here it maps these continuous outcome variables here could be things such as, so before in our classification example in the previous slide, we had the example of whether or not they had treatment-resistant depression, 0 or 1. So 0 or 1 in the previous example in classification, 0 or 1 was an example of discrete outcome variables, 0 or 1, it's binary. Whereas here, we're going to use continuous variables. So this is then regression. So here, the y vectors, so here the outcome y vectors it's going to be a continuous variable, such as the GAF, the GAF score of the patient. So this is the global assessment of functioning of the patient. So that is a continuous variable. And here we'll just label all the GAF score that corresponds with each patient and their features, and their symptoms, and their diagnosis, what have you. So we want to learn this function f. We want to learn this function f that mapped input x to the target outcome variable y, and this is regression, and here's the equation. Next, we'll talk about clustering. So what's clustering? Is it supervised or is it unsupervised? If you said unsupervised, that's correct. So clustering is a form of unsupervised learning. So clustering is about taking an input matrix X. Again, every row here is a patient, so we'll call it patient standing out. That's P. And every column is a feature. We'll say it's a disease. Okay. We want to learn a function F1 that partitioned this matrix into multiple clusters, P1, P2, and P3, and F2 to D1, D2, and D3. All right. So in F1, each cluster consists of a set of patients, and those patients are similar to each other, and those patients within a cluster, so those patients within a cluster will be different from patients in other clusters, right? In F2, what we do is we differentiate based on disease phenotypes, right? So here on the F1, where we go to P1, P2, B3, this is an example of patient stratification. Whereas the bottom one is an example of computational phenotyping. And I'll go more into that later. So how do you measure the performance of these algorithms? So for classification, what you can do is build what's called a confusion matrix. So in this confusion matrix, you'll see here where you can actually figure out what is truly positive and what are true negatives. So you want basically in an accurate classification algorithm where you're, in our example before, we were labeling something 0 or 1, 1 being treatment-resistant depression, 0 being not having treatment-resistant depression. We want to be able to compare the true condition, what's actually true, to the predicted condition, which is our algorithm. So in our algorithm, we want to figure out what is the true positive if they're positive, and what are the true negatives if they're actually negative, right? So when you start getting into errors or inaccuracies of your classification algorithm, then you start looking at classifications that fall in this false positive range, where you predict that a condition is going to be positive, such as 1, when it's really 0. So that's called false positive. That's a type 1 error. The other thing you can do with a binary classification system such as 0 or 1 is that you might end up having a false negative or type 2 error, where you predict the condition is negative but it is actually positive. So that's a false negative type 2 error. And then there's these other things that can help you determine other statistics regarding how well your model is doing, like with accuracy, which is the sum of the true positives plus the sum of true negatives over the total population. You could look at prevalence, positive predictive value. So all of this you can gather from what's called this confusion matrix for classification to measure performance on binary classification. You can also have these confusion matrix for things that have more than binary classification. So you might have 10 classifications, and then this confusion matrix would then increase accordingly, not just this 2 by 2, but it'll increase according to how big your different classifications are. So with regards to measuring performance for regression, what you can do is look at the R squared, which is the coefficient of determination. So closer to a 1 for R squared indicates the regression line perfectly fits the data, and closer to 0 for R squared, the coefficient of determination, closer to 0 indicates the regression line does not fit the data at all. You could also look at things like the mean absolute error, MAE, or the mean squared error, MSE. So this is the error between the prediction and actual value. This is small for low errors and larger for high errors. So these are ways to measure performance of your regression models. So how do you measure performance of clustering? Or you can use what's called the RAND index, the RI. Closer to 0 means a bad clustering assignment. Closer to 1 means perfect clustering assignment. So that's algorithms. Next, I will talk about how these algorithms can solve psychiatric problems via Psychiatry AI applications. So for predictive modeling, it is about using historical data to build algorithms to predict future events. For example, we could predict which treatment is likely to work for a patient with depression. So for example, let's look at patients with depression who responded to treatment. So Group A responded in the first 2 years of treatment. Group B responded between 2 to 5 years of treatment. And Group C continued to suffer even after 5 years of treatment. So predictive modeling would help improve matching patients to the right treatment quickly so that the late responders in Group B will become early responders in Group A. Right? So let's just look at Group A. So whatever you're doing for Group A, you're actually already classifying them as early responders. So you're doing a good job there. Don't change what you're doing for Group A. Keep doing what you're doing, okay? So just keep doing what you're doing for Group A. Don't change a thing. However, you want to look at Group B and Group C because actually what's happening is Group B is not responding. They only respond after 2 to 5 years of treatment, and then Group C, they're out of luck because they continue to suffer even after 5 years of treatment. So you got to do something different with Group B and Group C. So with Group B, you can actually use predictive modeling to try to match patients quickly as early responders. So basically, out of Group B, there has to be something in there that you can pick out that you can send them to treatments so they can become early responders, right? So you can use predictive modeling to help you do that, to send them actually to the right treatments, because probably in Group B what's happening is if they responded in the first 2 years of treatment, probably what's happening is the psychiatrist or doctor is actually putting them on treatments that aren't working initially, and then they finally find the right treatment, but it took them up to 2 years to find the right treatment. So what if you just took Group B and use predictive modeling to match the right treatment quickly, so you don't have to wait 2 years, then you can just take the right treatment initially so that you can respond faster and become early responders. So that's how Group B can be assisted with predictive modeling using machine learning to match Group B, match them to the right treatments quickly. Okay. However, with Group C, you're not. This is bad because up to 45% of this population actually didn't respond at all. They continued to suffer from depression even after 5 years. So we got to do something about this group. So with predictive modeling, maybe we can match these patients to new treatments quickly. So this one is about actually finding maybe not going with first choice treatments, but actually finding new treatments for these patients. So these could be treatment resistant depressions that they might need combination treatments with different medications, with different forms of therapy, with combinations of medication and therapy. Maybe they need hospitalization. So basically you can use predictive modeling to match to new treatments quickly, right? And then eventually once you find these new treatments matched to the appropriate patient in Group C, then eventually they can also become early responders as you start to match them to more effective treatments for this treatment resistant group. Okay, so that's an example of how predictive modeling can help patients in Group B and Group C actually respond to treatments quicker and become early responders, such as those in Group A. Okay. Computational phenotyping is another form of AI that can help with psychiatric problems. So the input to computational phenotyping is the raw patient data. So here we got the raw patient data, demographics, diagnosis, medication, procedure, psychotherapy, clinical notes, lab tests, psychological testing. So these are all raw data that we could feed as input to computational phenotyping. So again, and then we mentioned the different sources in addition to clinical notes. So the phenotyping is the process of turning the raw patient data into medical concepts or phenotypes. Right? So here, phenotyping, it's a form of data mining. And then what happens is, with this data mining of the patient, the raw patient data, we can mine these patient data and then turn them into medical concepts or phenotypes. So this is called computational phenotyping. So this might actually help us to look at new subtypes of disease. For maybe it will identify new subtypes of depression, new subtypes of anxiety. So it might give us some subtyping of psychiatric disorders that we haven't seen before because we haven't seen the patterns and are stuck in our old ways with regards to DSM-5. So computational phenotyping holds great hope in psychiatry to help us determine some phenotypes we haven't seen before or haven't really categorized before, but this is actually just looking at it from a data point of view. Okay, computational phenotyping holds big promise for psychiatry. The next type of psychiatric AI application is called patient similarity. So when treating patients, doctors often compare the current patient to past patients they have seen. So this is also known as case-based reasoning. So patient similarity is about simulating the doctor's case-based reasoning using computer algorithms. So instead of depending on one doctor's memory, wouldn't it be nice if we can leverage all of the patient data in the entire database? So when a patient comes in, the doctor does an examination of the patient. Right? Then based on that information, we could do a similarity search through the database. So we find those potentially similar patients, those similar patients to the patient that we're seeing, then the doctor can provide some supervision on that result to find those truly similar patients through this specific clinical context. Right? Then we can group those patients based on what treatment they are taking and look at what outcome they are getting, right? Then we can recommend the treatment with the best outcome to the current patient. So maybe we look at the patient database and use patient similarity, and then we see that, this group of patients taking medication has a positive outcome. This patient with therapy actually has a bad outcome, and this patient with exercise has a worse outcome. It's behind my video, sorry. So this actually has a worse outcome. So we're going to pick then the outcome that is best. So we're going to treat medication in this instance to have a good outcome. So this is just an example. I'm not saying medication is the best treatment, but for this example, it's just for example only. Okay. In this case, I'm picking this. So that's called patient similarity, when you use your patient database to assist with having them look similar, trying to find patients that are similar to them in the database with the doctor supervision. Patient similarity. So how to use patient similarity in clinical practice. Okay. So you have a patient and say you diagnosed them with a disorder and you ask, is there a guideline available? If the guy, so say your patient had depression and say you ask if there's a guideline available, yes, there are guidelines available for depression, then you use the guideline. However, say if you have a patient that comes in say they had depression, but it didn't really respond to treatment. Say they were, remember the example I gave you earlier, where the patient was in group C, where they didn't respond to any treatment. So now they're treatment resistant depression. So are there guidelines available for this patient? Not really. Um, then you can ask, are there similar patients? You can use patient similarity. So maybe you want to look at the database, and if it's yes, uh, you can use patient similarity to see what treatments work for those other patients that look like your patient that is treatment resistant. So if the answer is yes, use patient similarity. If the answer is no, then you're left with clinical judgment, right? So here is where you can then, so for guidelines that are not available for a particular set of patients, you can start to develop this, build a database of these patients that have no guidelines, and you'll either use patient similarity or use clinical judgment. So after a while, you might develop hypotheses about what the cause of this treatment resistant is, and based on what you're using with patient similarity and with your clinical judgment, the treatments, you might develop a hypothesis. And with that hypothesis, say you are coming up with a different combination treatment that helps with treatment-resistant depression. So say you're using a special form of therapy with a special medication that's used for other things, and that this helps for treatment-resistant depression, and you want to test this. So you come here and see if is it ready for a randomized controlled trial. If so, then you perform the randomized control trial, and if you have positive results and you can replicate it, then pretty soon you have guidelines available, and then for treatment resistant, then you could say yes, then you use the guideline. So this is how you can use patient similarity in clinical practice, which then can lead to hypothesis for those that we don't know how to treat and don't have guidelines for, and then develop randomized control trials to perform the RCTs to then eventually have guidelines for those patients that previously did not have guidelines. So this is the roadmap for how you use patient similarity in clinical practice. It just improves it. So what about the perils of machine learning in psychiatry? You know, there's psychiatrists are a funny bunch. Um, they like to hold on to tradition. Um, Here's some quotes from some prominent people in psychiatry, and let me just quote it here. So, the perils of machine learning in psychiatry. Quote, there have been so many fads, and we've discovered the ultimate answer in psychiatry 1,000 times. Machine learning could just be another one. Okay, and another one. Here, the biggest challenges are sensitivity and specificity of an algorithm's predictive results. Ultimately, the results of any algorithm must be replicated across different datasets. So, quote, this is a particularly important challenge as a medical test must apply to all potential patients, or if not, it must be very clear for whom the medical test is informative, end quote. So, the first quote that this is a fad, I don't think so. This is real. Um, Machine learning is helping other professions, and you know what? Medicine and psychiatry are late to the party, unfortunately. So you guys are late to the party. You guys need to get with the program and embrace machine learning and big data, because guess what? It's transforming the other fields, and medicine and psychiatry is late to the party. And the more you resist machine learning in the clinical practice, the more behind you will get behind, and then yet again will external factors then determine the fate of psychiatry, right? So this is just, this type of thinking is because you don't really understand what machine learning is about. So therefore, you have to rely on experts such as myself, who are both. I'm both a clinical researcher, a psychiatrist, of more than 15 years of clinical experience, and now I'm a data scientist, and I actually do data science. I work with data and I build algorithms every single day for machine learning AI applications. So um, don't listen to psychiatrists that don't know anything about AI and machine learning. Listen to psychiatrists who actually know something about AI and machine learning, and I would be one of them. So it's not a fad. So just look at the other fields where machine learning has transformed. So machine learning can enhance psychiatric practice. It can inform. Machine learning can inform hypothesis testing for future clinical trials. It could complement. So machine learning and RCTs actually complement one another. It can augment. Machine learning is not meant to replace RCTs and clinical guidelines. It's meant to augment it, right? And it can help. Machine learning helps for patients not covered by the RCT groups and clinical guidelines. So machine learning can enhance medical psychiatric practice. It will not replace it, okay? It can enhance and augment. So have no fear. You as the psychiatrist are still very important to psychiatric clinical care. However, machine learning could just help and augment your practice. It won't replace you, okay? So I just want to get a little bit into neural networks and deep learning. So a neural network is basically where you have these inputs. So you have these input nodes, and you'll have these input nodes which actually connect to hidden nodes, right? And then from these hidden nodes, you have outputs and your outcome variables. Okay, that's a neural network. It's a simple one because it only has one hidden layer. However, when you have deep learning is about having multiple hidden layers. So the more layers you actually put between your inputs and your outputs, the more complex your model, your neural network becomes. So this is called deep learning, when you're actually looking at these input nodes going to each hidden layer, and in turn each hidden layer then goes to different hidden layers here. So you see how this is mimicking the human brain, right? These neural networks, and deep learning is where you have multiple hidden layers. Okay, so that's just a little about neural networks and deep learning. So finally, you're going, so what? You presented AI, you presented big data in psychiatry, you presented big data systems, Hadoop and Spark for psychiatry. You even presented some algorithms, supervised learning, unsupervised learning, regression, classification, clustering. I mentioned some psychiatry AI applications such as patient similarity, such as computational phenotyping, right? Predictive modeling. Yeah, so what? You say, at the end of the day, I just want to see patients and I want to diagnose them, I want to treat them. Okay, well, if that's what you want, then that's what you'll get. So my team was involved with actually training an AI to actually make diagnosis from clinical notes that I made up. And so I had made up hundreds of clinical cases with diagnosis, and basically fed these clinical cases and painstakingly labeled them, and then fed them to a deep learning model to help me come up with diagnosis just by entering clinical text. So here's an example. So Anne is a 19-year-old single Caucasian female who's attending university and works part-time as a cashier for a pizza restaurant. So she has a history of recurrent depressive episodes, which starts in the late fall or early winter months and remits during the spring. So basically, I just detail here a typical patient encounter, right, in text. And then again, my team built an AI application where we can take this clinical text, right? So this whole clinical text. So we'll skip this part as this was a video of the app. I'll go to the next slide. So I gave you that example of Anne as a 19-year-old female, and she's attending university, and she has a history of recurrent depressive episodes. So I showed you in the previous slide that the clinical notes for N, who's a 19-year-old female who has depressive symptoms. And so when I input this text into this AI app, it comes out with a diagnosis, says the diagnosis major depressive disorder. And then next, not only does it give a diagnosis for the inputted clinical text, it also gives the overall risk factors for the patient. So with regards to vulnerability, so here the patient apparently has a lot of vulnerabilities. So this could be things such as maybe she has poor support systems and therefore is very vulnerable, or maybe she's homeless because of her illness and therefore has vulnerability. So here, vulnerability is high for her. Another risk factor for her is harm to others. She has mentioned there's some things here about wanting maybe thoughts of harm to others. Here's some issues with engagement. Maybe she's not going through a therapist. Some issues with alcohol and drugs. Minimal self-harm ideation. So not only will this AI app that's trained on labeled mock patient data, not only can it give a diagnosis, but could also give some risk factors that goes along with the diagnosis. So this is just an example of how an AI application for psychiatry could be clinically applicable. I'm not saying that this AI app is ready to be used clinically to assist doctors, family doctors, with diagnosing psychiatric disease. I'm not saying that, because this still needs to be validated and tested as any medical device. But what I'm saying is we're at the point now where we can train these AIs to make initial impressions with regards to diagnosis, with regards to risk factors, and also with regards to treatment planning. So you can see the potential for this with psychiatry, because there's just a shortage of psychiatrists worldwide. And imagine an app like this in the hands of a general practitioner or a family doctor. Then they could, because they don't have enough psychiatrists to consult with them, they can rely on apps which are extensions of us to actually help them with psychiatric diagnosis and treatment planning. And of course, this is not meant to replace doctors. This is meant to assist. So in that example I just gave for this app, this can help with general practitioners and family doctors to make initial impressions. And still, they're probably going to, even if they say this patient likely has major depressive disorder from this app, then they still have to make the referral for confirmation. But just imagine something like this, that maybe the referrals from your family doctor will be more fruitful than how it's going now, so they can make better use of the psychiatric consultants they have, rather than just giving you everyone. They give you cases that psychiatrists can actually treat. So say you had a patient like this and presented to the family doctor, and it stated that they had major depressive disorder from this app, then they can make the referral to the psychiatrist, and this would be a more appropriate referral, rather than just referring something where the patient doesn't have any mental illness. But in a family practice setting, differentiating between mental illness and not having mental illness is actually quite challenging. So having something like this as an app for those family doctors would actually help out psychiatry in general, because family doctors just don't have the training for this, right? So they need all the help they can get, and there's not enough of us to actually consult with the family doctors to make the determination on the mental health status of their patients, right? So again, I'm quite passionate about AI and big data in psychiatry. I think it has great potential for transforming the clinical practice of psychiatry. And again, don't listen to the naysayers. It's not a fad. This is real. You're seeing it in the Green Journal. You're seeing machine learning, deep learning, AI applications coming on board. There's Wobot that's has research studies behind it showing its effectiveness for depression and anxiety, sleep problems. So, and then my team has built an AI prototype for psychiatry, and hopefully we'll get into the testing and validation phases so we can hopefully have this as an option for family doctors to help with psychiatric diagnosis and treatment planning. So that's the hope. This is real. This is not a fad, and it's here to stay. So if you have any questions regarding AI and machine learning, big data in psychiatry, please contact me. You can reach me via email at carandangc@gmail.com, or you can go to my website, carlocarandang.com, and you can reach me that way. And thank you very much for listening, and have a nice day.